flowing through some device, some material perhaps, dependent on what potential difference we apply across, let's say, the sides of that device or the sides of that piece of material. So this is our definition of resistance. Which is the quantity that relates the current and the potential difference across here. So what about units? So as usual, volts, amperes, and since this is sufficiently common new quantity that we're going to introduce, we're going to give it a new name. So this is our definition of the ohm for resistance. Okay, so 1 ohm, I'm sure all of you have seen this symbol before, or capital omega in the Greek alphabet. 1 ohm is defined as 1 volt per 1 ampere. So this now is a measure of a material or device's resistance to current flow. All right. So we started before the break introducing some circuit symbology. We're going to continue that now and introduce the symbol for a resistor in a circuit diagram. A couple of possibilities. The more common one, I would say, is this. It's kind of like a representation of an up and down kind of coil almost. So this is one representation for a resistor. Less common, but you'll certainly still see it as well. It's simply that. Okay? So whenever you see either of those two symbols, we're talking about a resistor in circuit setting. All right. So we've defined resistance based on really some macroscopic quantities, current and potential difference applied. Again, it's useful to look maybe outside the context of a particular device and look at this simply based on material properties, and that leads us to the concept of resistivity. Okay? So for resistivity, and again, this is for specific materials. So we're often interested in the resistivity. And in this case, I'm going to throw in a second definition. That. So this now is the resistivity, and defined here in terms of the electric field and the current density in the material. Okay, let me just throw in a couple of pieces of general information. We've talked already about idealized conductors and idealized insulators. So for us, we've kind of been assuming that in the case of conductors, there's no resistance to current flow. And conversely, in the case of insulators, we're assuming that there's infinite resistance to current flow. In reality, we're never quite as extreme as that. So some practical values for actual materials. So let me just give you some typical numbers here. So we'll look at conductors, common materials, insulators. And I'm going to throw in here, though we won't have a chance to talk much about this in this course, unfortunately, something that by definition, or certainly by the naming of these materials, semiconductors are somewhere in between. So in terms of conductors, we're typically looking at resistivities that are maybe of order 10 to the minus 8 or so. And I'm going to throw in the units here, which I'm just going to come back to and make sure you understand where that comes from in just a moment. So we're looking at resistivities that are very small, 10 to the minus 8 for conductors, as you would expect. Insulators, by contrast, these may be of order 10 to the 12 ohm meters or more. So you can see huge orders of magnitude differences between typical conductors, typical insulators. And then semiconductors, again, we won't have time to talk too much about these, but they often span the range of about 10 to the minus 3 to 10 to the plus 3 ohm meters. Okay, and as you would expect, that interim. They also have very interesting, for example, temperature me just look at units here to make sure that this makes sense. So we've got this as E over J. So in our relatively newly introduced units of electric field, the volts per meter. And for our current density down here, we have amperes over meter squared. We work this out and then throw in our new definition of the ohm based on this over here. You'll see that we get resistivity measured in ohm meters in SI units. Okay, so just make sure you're comfortable with that unit manipulation. It's pretty straightforward. Okay, so now we've got definitions of macroscopic resistance for particular devices, material-dependent resistivities. One other thing I'll throw in, though I probably won't use it at all in this class, so I'm going to put it in parentheses. You'll sometimes find people using conductivity as opposed to resistivity. This is simply an FYI only. And conductivity is defined as the inverse of resistivity. Okay? So just to be confusing, this now is the conductivity and it's 1 over the resistivity. Okay? So I'm not going to use that, but some of you may come across instances where conductivities are defined. Okay, so let's take this and see if we can quickly do a simple back and forth to figure out the relationship between the resistance of a particular resistor that has a certain geometry that's made up of a certain resistive material. So we're going to relate the resistance big R with the resistivity rho for a particular device. So I know we're moving relatively quickly here, but it's fairly simple stuff. And to get on to slightly more interesting things. So relating R and omega for a specific device. So let me take the thing that I had a moment ago. I think I've erased it at this point, which was a cylindrical device. It's resistive in nature. So I'm going to give it again a length 8L. We're going to be driving a current I through this thing. And as before, we have a cross-sectional area A. So exact same setup. We're also going to assume that there's a potential difference, and at this point you see I'm dropping the deltas, but I always want you to remember let's talk about the potential difference from one side to the other. We've got a potential difference of V across this thing. Okay, so let's see what we can do to figure out a relationship between these two quantities. Let's first off assume a uniform current. J is the same everywhere through here. Okay, so what do we know if these assumptions hold? Firstly, I'm going to claim that I can write the electric field as simply, well, let me do it in a way that kind of looks familiar from before the break to begin with, maybe like this. So I'm going to write this as negative of the potential difference over a distance here. And so in terms that are actually more relevant for our particular setup now, this is just V over L in terms of magnitude. That's pretty straightforward. I know that the current density is I over A. So I've got an expression for E, I've got an expression for J. I'm going to combine these in our definition of resistivity, which is now E over J. So this becomes V over L in the numerator and I over A in the denominator, which is to say that it is simply R times A times L. Let me finish this up. I'll step back and talk about it. I'm going to rearrange this, and it now tells me I have this relationship between the resistivity and the resistance, okay? So again, I know I'm going quickly here, but let me just quickly recap. We've got a particular device, cross-sectional area, known length. We apply a potential difference across it. In terms of our definitions from before the break, we know we can define electric field as being the negative of a potential difference over some length element. It's a uniform electric field, it's constant, so we're just going to write this as a voltage drop over a length. Our standard definition of the current density, plug and chug, and we end up with this relationship, which finally gets us to this, okay? So what is it telling us? Probably something that is fairly intuitively straightforward. This is material specific, depends on the material, but once we're given a material, we find that the resistance is proportional to the length which we're driving the current through, and it's inversely proportional to the area. Okay? So think of this whichever way you will. It's the sort of visual picture I often have here is, it's kind of like trying to drive toothpaste through some particular aperture or something like this. If you imagine trying to do this, the longer the thing you're driving it through is, the more resistance it puts up to the motion of your toothpaste in this case. And if you open up the cross-sectional area, you simply widen the aperture. Of course, it's much easier to get the toothpaste through. So the resistance in this case goes down. Okay? So this geometrical picture is very straightforward, and it sort of behaves in a way that we would expect. All right, so I know we're racing through this, but any questions on these sort of simple definitions and relationships for resistivity and resistance? Okay, so what I would like to do is now talk a little bit about what's called ohmic behavior, Ohm's law. Some of you may have a slightly, it's a little more nuanced to this than we're often told the first time we do electrical circuit analysis. So let me talk a little bit about ohmic behavior and Ohm's law. So, quick reminder, we've defined the resistance of some object, some device as being the relationship between the potential difference applied across it and the current flowing through it. Typically, we might simply measure this for certain types of devices. And so we may take our device like this, we're going to apply a potential difference, and we're going to simply measure what the response is. So let's apply a potential difference across here. We're going to figure out what the current is going through it. So there are, it turns out, for various types of devices, various types of materials, lots of possible outcomes to these types of measurements. So I'm going to show you the very simplest one to begin with, which might look something like this. So I'm plotting the current observed passing through this device as a function of applied voltage. Okay. So, that green line. Pass that green line for me and tell me what that tells you about this material. Yeah?
The resistance.
Okay. What else in terms of the shape of the green line with its behavior in all areas of the plot?
It's linear.
Yeah. Okay. Anything else? If you look at this, it's obviously got an origin. On the right-hand side of that origin, I'm applying potential difference with a certain polarity. On the other side of the origin, I'm flipping the polarity.
The area under the curve is the power dissipated by the resistor.
Okay, let's not get onto that just yet, but in a few minutes. Just tell me a little bit, anything else obvious about this in terms of its behavior on the right side and the left side of the origin? Okay. Okay, good. All right, So, I mean, this seems obvious, but first off, it's linear. So that tells us that V over I is a constant. Okay? And in fact, this is actually Ohm's law. It's saying that V over I is constant regardless of the applied voltage. I imagine some of you want to tell me that V equals IR or R equals V over I is Ohm's law. It's not. Ohm's law is the fact that this is constant and that R is constant. Okay? So that is Ohm's law. It's the constant that makes this Ohm's law. Okay, so first off, it's linear, fine. Secondly, it's symmetrical, depending on polarity. So it's symmetrical with respect to, this is what WRT stands for, with respect to polarity. So I see the same behavior regardless of which way I apply my potential difference. So this is an ohmic material. So these two things together make this an ohmic device, I should say. So maybe device specific rather than material specific. That seems obvious. There are plenty of other devices or even plenty of other materials that might have different types of responses for a current versus potential measurement. So for example, if I was to take a different type of device and made these series of measurements and I saw something like that, well, just tell me first off, what are the characteristics of this one compare and contrast with the previous one? It certainly doesn't follow Ohm's law. It's not linear. And what about the left-right behavior? Positive, negative potential difference. Symmetrical or no? Definitely not, right? So not symmetrical. So this is obviously not an ohmic device. Some of you will know this. Just take a look at this and look at what are the general characteristics of this, and is there a sort of name that we might apply to it? I'm not even going to define a particular shape there. It's just not linear. That's all I care about. But anything that's specific about this kind of asymmetrical behavior. It is. It's a diode. What's a diode? Anyone know? Yeah. So a device that only allows current flow in one direction. So this would be a representation of, it doesn't have to be a diode exactly, but a diode would have, for example, these types of behaviors. So this is clearly no longer symmetrical. It only allows current flow in one direction. So this is most definitely a non-ohmic device. So whenever we talk about ohmic, again, what I want you to really emphasize is this. I mean, of course, it's true here that what we will define as the resistance is still V over I at any point, but it is no longer constant, okay? So that's what makes this a non-ohmic device, whereas this one over here is an ohmic device. So just be aware of that distinction, because it's often the source of a little bit of confusion. All right, good. So let me spend the next 10 minutes or so coming back to looking at things in a small scale. And then we'll talk about power in electrical circuits. Okay, so. I want you to think back to that picture we've described twice now of what charge carrier motion in something like a metal actually looks like. Don't worry about this name, but I just want to throw it out there because you will often hear about this otherwise also called the Drude model, free electron model. So what are we looking at here? We're looking at a typical conductor, to make it a metal, comprising a lattice of fixed positive nuclei surrounded by what's often described as a sea of free electrons. Now, as we started off today's session sort of describing, the picture I want you to have in mind now is that these free electrons are moving randomly at very high speeds. They're colliding very often with these fixed atomic nuclei. They bounce off them in random directions. And so that's what's happening in the absence of an external electric field. We then apply an electric field, and superimposed on that random, very fast motion is this slow drift of the entire bulk of those charge carriers. Okay? 10 orders of magnitude more slowly than their average random speeds. So, let's see if we can quickly sort of imagine what's happening between these collisions. So these free electrons are moving with, I'm going to call this an effective speed, Vf, of around 10 to the 6 meters per second, colliding frequently with fixed nuclei and bouncing off. If we then apply an external electric field, so first off, think about this. Aside from this random motion, we're now applying an external electric field. In terms of Newton's law, we should expect that there's an acceleration on our charge carriers. So we're going to describe this as simply F over m, Newton's law. And if we've got charge carriers that simply carry a charge E, let's describe it like this. So it's the charge on one of our electrons, which is little e, multiplied by the electric field strength, big E, over the mass. So that's the acceleration these electrons experience once we put them in an external electric field. Now we're going to say, let the average time between collisions conventional to call this tau rather than t, because it's very much specific to time between collisions in this sort of Brownian motion chaotic system. So we're going to define the average time between collisions to be tau, and these collisions are independent. So it really is random motion in terms of collisions. Chalkboard here, you can see everything. This next step's a little bit subtle. Okay, so come up here. Let's say we're going to again go back to kinematics and Newton's laws, and we're going to say that something like this. Okay, so we've now got our objects in motion, electrons in this case, experiencing an acceleration. That's this thing here, and on average, they're experiencing an acceleration for a time tau before they collide with another nucleus. So to guess is the average speed of all of these electrons before we apply our electric field. And this is a vector. It's important. Zero. Why?
They all cancel out.
Right. It's random motion, Brownian motion, thermal motion. So it's, we just get cancellation because it's random motion. So in fact, the average velocity of our electrons is simply the sum of these two terms. Sum of the averages of the above two terms in my kinematic equation. So this one we claimed is zero, so in fact this simply tells me that the average velocity is the acceleration times tau. Okay? Alright, so if we've got this, now I'm going to say that I'm going to substitute A from over here. So I'm going to write this as E times big E over M times tau. That's my average speed. And if you think about this, now this is the average speed once I've applied my external electric field. This is exactly what we called the drift speed a few minutes ago when we were defining drift speed under the influence of constant electric field. So this is in fact the drift speed. So what I'm going to do is just equate this to what we know for the drift speed. So we know that J equals NEBD, that's what we derived half an hour ago. So we know this is, again, moving fairly quickly, but let me just write this down, and then once it's all up there, we'll step back and summarize and see if it makes sense. So remember, I have this. I'm going to take my drift speed. I'm going to define it as J over NE. That's this. I'm going to equate it to this. So these two terms become equated. And then what drops out of this is that I can write J over NE equals E big E over M tau. Almost there. I'm going to finish this up over here so everyone can see it. And this tells me now that E equals M over N E squared tau times J, where this is just the resistivity. Okay, so I know a lot going on quickly here. Let me summarize it quickly. I'm going to pause for questions, then we're going to talk about the results and see what it tells us. All right, so we've got this picture in mind of random collisions between electrons and stationary ions. So the average speed in terms of a vector quantity is zero. Then we apply an electric field. We are assuming there's an acceleration just based on the Coulomb force on the charge carriers is the acceleration. Now we're saying that the average time between collisions is tau. So that's the time in which our charges can be accelerated before they smash into another nucleus and they move off again and then they're accelerated again. So it's this continuing repeated process. We're going to try and look at what the average speed is by looking at this term and this term. We've already claimed this one is zero. So in fact, the average speed after this time between collisions, tau has elapsed, is just this. So it's A times tau. And then, let's see, there's my A in here. If we go back to our definition of drift speed, claiming that these are one and the same thing, of course they are. It's the average speed of motion of the charge carriers. This is how we derived it half an hour ago, in terms of the current density and the charge carrier density. Equate these two things, and we're left with this, okay? So this, of course, is the exact same relationship we had a few few minutes ago, where we had defined the quantity in parentheses as being the resistivity. So now we've figured out a way to relate the macroscopic resistivity with a bunch of microscopic parameters. So this is the value of the free electron or Gruner model, and it allows this relationship. Okay? So, does this give you much physical insight?